In this video, I'm trying to explore what Wav2vec 2 is, and this is the official Hugging Face page where the Wav2vec 2 model documentation details are given and how to use it. The steps are pretty straightforward, and it is by Meta Facebook. But in this video, I'm looking for the architecture. So let's try to see what is inside this Wav2vec 2 model. Let's try to understand and decode its architecture. For that, I have this blog, illustrated tour of Wav2vec 2.0. Okay, so first of all, let me get this clear that Wav2vec 2 is the second version. The first version is something called as Wav2vec. That's it. Uh, this is its research paper, Wav2vec, and this is the second version of it, Wav2vec 2. Now, this is a good paper. What we are going to try to do is we'll go through it. They have divided the architecture into four parts, and those four parts are feature encoder, context network, quantization model, and contrastive loss. They have also compared it with Kaldi, which basically uses the phones as a basic single unit of the voice, phones, phonations, which is uh, a single occurrence of a sound. It's a single unit of a sound. So they have compared with it, and they've also explained how this is different from the conventional method. Wave2vec 2 has basically many use cases, and one of the most used use cases is ASR. So let's try to walk through this paper or this blog, and let's try to see how they have constructed the architecture. Okay, there are four important elements in this diagram. First is feature encoder, then is context network, third is quantization model, and fourth is contrastive loss. Now let's see what feature encoder is. Basically, in this, what they are trying to say is they have divided the audio into 20 millisecond fragment, and then they have created a 7-layer convolution neural network with 512 channels, and this is their architecture. What they do is basically this waveform is normalized, and after normalizing it, the flattening is done, and there is a 7 convolution blocks, which gives me this latent feature vectors. This is the output, which then goes into our second element, which is quantization model. This is input. This thing is input to our quantization model. So the end goal of this is the latent feature vector, which are of 512 dimensions. Uh, they have also given that the 25 milliseconds of audio was sampled at rate of 16 kilohertz. Moving on to quantization model, what they are doing here, this latent feature which they are multiplying it with quantization matrix, and it gives them code group 1, code group 2. What is code group 1, code group 2? So what they have done is in code books, which is a huge data of words and sounds. So what they have done is uh, they are multiplying the output of that audio module from feature encoder module, this latent feature of 512 dimension, with quantization matrix. And basically, they have divided it into two groups. Group 1, Group 2, both have 320 possible words. And this is the speech unit which we get, 102400. And what they have done is it gives you logits. And on this logits, they use Gumball Softmax. Gumball Softmax is basically your argmax plus softmax. So Gumball Softmax is basically what they do is it is a variant of softmax, but also uses argmax with it. So it maximizes it. And then what we do is we get this output value, and this output value is later on, yeah, so it is similar to taking argmax, except the population is fully differentiable here in Gumball softmax. And then what they try to do is in this uh, paper that they take this word and then multiply it with quantization projection matrix, which gives them a final quantization vector. Coming to their third module, which is context network. This is basically a transformer, but only uh, bird side, so an encoder side, because they have mentioned here that it is similar to birds masked language model. So here what they are doing is the core of is transformer encoder, as you see, only encoder part of transformer, and BERT is also only encoder. So bidirectional encoder is your BERT, and here also they are using only encoder part. Now they have given few details about the architecture, like they have 24 blocks and 512 dimensions, and then 768 and then 1024 for large. This is for base, this is for large. After this, what they're trying to do is uh, the transformer architecture is giving them this output, which basically goes into their contrastive loss, and here pre-training is also done. The important thing about this is they use masking technique. So what they do is they basically mask 50% of their latent vectors, and after masking them, so if you can see here, they have randomly masked 50% of the latent vector head, and your latent vector is basically your output of feature encoder, the first module. This gives you output your latent vector. So they are masking it randomly, 50% of the masking is done. And then what they are doing is with cosine similarity, they are computing the uh, similarity between this output, which is your output of uh, this module, the context network module, C0, C1, CT. So what they are doing is basically they are comparing this with the masked module, and then with help of cosine similarity, they get the similarity, and in this way, the ASR module is tuned. In paper, they are using CTC loss. CTC loss is where you try to get the each level you try to get it with the word, and this is also called as connectionist temporal classification, because every phonation has the wordings, and what they're trying to do is they're trying to match it. So this is the CTC loss which they are using and is also mentioned in their paper. So right now this is all for this video. Here you can find the original paper. What I'll do is I'll add all the links to the description of this video. But for this video, that's it. Hopefully we'll meet in next video. Thanks.